The next topic, ladies and gentlemen, is the power density spectrum of periodic signal. Now, in order to determine the power density spectrum, first of all, we must discuss a little bit about the energy signal and the power signal in brief. Now, what is an energy signal? The energy signal is nothing but a signal which is said to be having energy, that is the total energy transmitted. I'm sorry, let me rephrase. The signal is said to be energy signal when the total energy transmitted is finite. So, the signal is said to be energy signal when the total energy transmitted to the load is finite. Mathematically, this can be written as total energy transmitted expressed as E equals an integral of minus t to t, where t being the time period, x square of t dt. This is obviously for a finite duration. Now, for an infinite duration, we get the energy signal to be, limit of the time period which ranges to infinity. The rest is same, an integral from minus t to t, x square of t dt. This is for the infinite duration. Now, from this expression, the energy signal can be defined as the energy signal is nothing but the integral of the square of the voltage. This is obviously the signal value x of t is a voltage value or an amplitude value or the magnitude value that is taken with respect to time. This can be over a finite duration or an infinite duration. Now, let us go to the power signal. What does the power signal say? The power signal is said to be, a signal is said to be a power signal when the total average power of the signal is finite. Both the cases, either energy signal or power signal, the total energy transmitted should be finite. In case of energy signal, the total average power should be finite in that case of the power signal. Mathematically, the power signal can be written as P equals 1 over t, where t being the time period, 0 to t, x squared t dt. This is for the finite duration. And for the infinite duration, you have guessed it right as well, it becomes limit. The time period goes to infinity, denoting the duration to be infinite. The rest is quite same. 0 to t, which is integrated for x of t dt. This is for the infinite duration. Now, upon closer observation, we can come to the term that the energy signal and power signal are two complementary quantities. By this, I mean that if a signal is energy signal, it can never be a power signal, or if the signal is a power signal, it can never be an energy signal. So, to summarize, a signal can never simultaneously be an energy signal or a power signal. From that, let us go to two assumptions, that is the power of an energy signal is always 0 and the energy of a power signal will always be infinite. Hope that is clear. Returning back to the power density spectrum, first of all, we must say the average power of a periodic signal over any period is finite. We shall come to this mathematically. So, as we have seen earlier, the expression of power signal P of x, which is 1 over Tp 0 to Tp modulus of x of t squared dt. Now a question might come to your mind, where does this 1 over Tp come from? As we have learned in basic physics that the power is nothing but an energy per unit time. So if the energy signal is this part over here, so the power will be an average over its time period Tp. Now this can be further expanded as 1 over Tp, an integral from 0 to Tp, the time period, x of t times x asterisk t, where it must be mentioned that x star t is the complex conjugate of x of t. Now, recollect your basic AC and DC circuit analysis course, where you have learned that the signal x of t squared can be written as x of t and it's multiplied by its conjugate counterpart. Now, if we give this equation number 1 implies P of x to be equal to 1 over Tp, an integration of 0 to infinity, Tp, x of t as it was, and taking the Fourier series expansion of x star t, or the conjugate of x of t. So the Fourier series expansion will be k, a running sum where k goes from minus infinity to infinity, the coefficient ck. Now previously the Fourier series coefficient was ck. Now since we are working with the complex conjugate, ck must also be the complex conjugate of ck. That sounded wrong. What I meant to say was that in the first case we used to work with ck. Now we should work with the complex conjugate of ck, and consequently there will be e to the power minus j 2 pi k f naught t dt, which is the basic Fourier expansion, that is the exponential form of Fourier series expansion. Now, as I have said before, interchanging the integral and the summation, the running sum, does not affect the outcome of this expression. So let us interchange that, where the running sum is taken outside of the expression, and ck, as it does not depend on this integral, that means ck, since it does not depend on time, it can be also brought out with the running sum. All we are left with is 1 over Tp integral of 0 to Tp x of t e to the power minus j 2 pi f naught k t and dt, since we are operating an integration. Now, ladies and gentlemen, if you watch very closely, this expression is quite familiar to us, which was the analysis equation by which I mean that this is the value of the Fourier series coefficient ck. Hope you could recall it. So this expression can be written as k, which runs from minus infinity to infinity, ck conjugate, and replacing this value with ck star times ck. This in turns become summation k goes from minus infinity to infinity, ck squared. So we have established a relationship that px equals 1 over Tp x of t whole squared dt equals the summation of k, which goes from minus infinity to infinity, ck squared. And for any value of k, this is obviously a finite value, hence proving the initial assumption that we have made before going to the derivation. Now, ladies and gentlemen, this expression that I have written over here is known as the Parseval's relation for power signal, and it is very important in solving our mathematical problems or examples that I will show you in the later part of this lecture. Okay, now ladies and gentlemen, it is time that we solve a mathematical problem on Fourier series. Let us mark it as example example problem 1, where we are asked to find the exponential Fourier series of the given waveform, where the waveform being is somewhat like this. This goes to omega t. This is our amplitude, or f of omega t, and pardon my drawing, is a sawtooth waveform, starts from 0 to 2 pi and 4 pi, and this value of the amplitude throughout the signal is A. Let us come to the solution of the problem. Now, considering the Dirichlet conditions, the first condition is that over a period of time, the signal must have a finite number of discontinuities. The signal is continuous over here in this period and have only one discontinuity in this region. So the first condition is obviously fulfilled. The second condition is the signal must have a finite number of maxima and minima. The signal has a maxima over here, a minima over here, and a minima over here. So, since the number of maxima and minima are countable, so the second condition is also regarded fulfilled. The third condition is that the signal must be absolutely integrable. That means if we take the area under this triangle, it will always be a finite value. A triangle cannot have an infinite area, since it is an enclosed surface. So all the Dirichlet conditions are fulfilled. So we can proceed forward in order to find out the Fourier series expansion. Before that, if we closely observe, the time period of the signal is t, which equals 2 pi. After every 2 pi angle or angular distance, the signal repeats itself. So the time period is 2 pi, and we must mathematically derive the model of this function, which is f of t. Now this part is a straight line passing through the origin, and the formula of straight line passing through the origin is mx, where m is nothing but our slope and x is the abscissa. I forgot the spelling, so let's be at that. This can be said to be the values of the x-axis. Now, if you can recollect, the definition of slope is rise over run. The rise is the value or the peak value to the difference between the peak value to the bottom value in along the y-axis. So it is A, and the run is the difference between 2 points from the x-axis, from the start of the x-axis to the maximum value. That is, here it is 2 pi. Hope you understand this. Otherwise, we can also say it to be the tangent of this value and this value. And x remain as it is. So in our case, f of t becomes the slope, which is a over 2 pi, and x here is omega t. Now let us solve for the coefficients. Of the Fourier series. Let the coefficient be Cn, which equals 1 over t, the time period, and an integral of f of t, which is this function or the signal function, times e to the power minus jn omega t dt, omega obviously being the angular frequency. And the integration limit will be 0 to t. This can be further replaced by 2 pi. I mean, the time period can be replaced by 2 pi as we have shown over here. So the integral limit also changes to 2 pi a over 2 pi omega t, which is our given function, times e to the power minus j omega t of j omega t times n d of omega t.